and welcome back to another extreme value theory lecture. In this lecture, what we're going to look at is a review of the first two topics in section 3 of the notes, so looking at the point process and peaks over threshold representations of extreme values. What we're going to do to begin with is review the main concepts introduced in these subsections, and then we're going to go on to look at how we can use our code to fit a peaks over threshold model. So to begin with, if I can share my screen with you. And if I make this full screen. So what were the main results introduced in these sections? Firstly, we saw that extreme values can be modeled as a point process on regions of the form 0, 1 by u to the upper endpoint of the distribution function of x. And what we saw was in the limit, as our number of observations got large and as that threshold was sufficiently high, that this point process could be represented by a Poisson process, and we derived the intensity function of that point process. What that intensity function gave us was that exceedances of high thresholds have a generalized Pareto distribution. So x minus u, given that x is greater than u, follows a generalized Pareto distribution with scale parameter sigma u and shape parameter psi. What we saw as well was that if we're considering exceedances of a higher threshold v, where v is greater than u, that the exceedances of v also have a GPD distribution, but the scale parameter is not the same between those two distributions, despite the fact that the shape parameter psi is. So in particular, the shape parameter for this higher threshold v is going to be sigma v equal to sigma u plus the difference in threshold times by the shape parameter. And in particular, the survivor function for these threshold exceedances is given by this expression, which holds approximately for finite values. And it's this application at finite levels that we're going to consider in the rest of this video, where we're going to look at applying this asymptotic model for threshold exceedances and assuming it holds exactly for exceedances of finite threshold. So coming back to some of the useful properties of the GPD that we're going to be making use of. Firstly, that the shape parameter psi is invariant to the threshold choice u. So no matter what threshold we pick to model above, our shape parameter should remain constant. The modified scale parameter is also invariant to threshold choice. So remember, our particular scale parameters do depend on the threshold value. But if we look above a low threshold u and rescale the scale parameters based on higher thresholds by subtracting psi times the difference between that higher threshold and u, what we get is this parameter sigma star, which is invariant to threshold choice. What we can do is use these to see how low we can pick our modeling threshold to use as much data as possible while maintaining the validity of this GPD model. Because if the GPD is valid, then these two parameters should be stable. Another property that we can use in much the same way is the mean exceedance size. So this should increase linearly with the threshold as the threshold is decreased. So the lower you set your threshold, the larger you're expecting your mean exceedance size to be, and you're expecting that to grow linearly with the drop in threshold level. And again, this property can be used as a way of picking an appropriate modeling threshold where we want to include as much data as possible without violating either of these conditions. So let's move on and actually use this to model some data. So all I've done already is gone to the course Moodle page, down to the activities section, and downloaded this file, week 2 fitting GPD Newlin, and I've saved that to my desktop. So if I open up that file now, you can see that there's lots of subfiles in here. We've got helper functions, which just contains some function definitions that will help us do our analysis without writing quite so much code. Main.r, which is what we're going to edit and complete this analysis with. The CSV file containing the data that we're going to be modeling, and also a solution file for if you don't want to follow through with this with me now. There's a README file as well if you'd like to take a look at that and try out this exercise before watching the video. So if we go ahead and double click on main.r, that'll open up a new RStudio session within that folder. And I will just take a second to make this a bit larger for you. View, zoom in. Okay, hopefully that's large enough. And if I scroll up to the top of this file, we can see what we're doing is we're considering the wave height data that was introduced in the very first lecture, and we're going to be considering fitting an IID generalized Pareto distribution to each of the wave surges and the wave heights. So to do that, we're going to need the package ismev, which we can load in by running line 12. And we're also going to need the functions from the helper functions.r file. So read those in using line 13. To load in the wave surge data, we can run lines 16 to 19, which just reads that CSV file. And then if we make a couple of quick plots of the data. So firstly, we're plotting the wave height every day. And you can see this has got some strong seasonality going in with it, but we're just going to ignore that in our analysis for now. We'll come back to that next week and see how we can handle it properly. And in the second plot, we're going to look at the wave surge each day. And again, you can see that there's some strong seasonality going on here. Again, we'll come back to that next week to see how we can handle it properly. For now, we're just going to ignore that. And finally, just to convince you that this is the same data set that we saw back in the first lecture, here's a plot of one against the other. So what we're going to do here is look at fitting a GPD above a range of thresholds and then look at the parameter estimates above each of those thresholds. And to begin with, we're just considering the wave data here. So in gpd.fitRange, where the data is equal to our vector of wave heights, the minimum threshold is going to be at 0, the maximum threshold we're going to try is 7, and the number of thresholds we're going to try is 20. If you run this line, then what you get is a pair of plots giving the estimate of the modified scale parameter sigma star and shape parameter psi when you fit the GPD model above a range of thresholds. So what you can see here is that for very large threshold values, the confidence intervals shown by the vertical lines are very wide. That's because we're not using very much data at all to estimate our parameters, so our estimates are going to be very uncertain. As the threshold gets lower, our confidence intervals narrow down because we're using more data in our estimation procedure. And what we want to do is look at how far back we can go, how low we can set that threshold, while being able to draw a straight line through all of the confidence intervals. And here it's probably somewhere around 2. And again, looking at the shape parameter rather than the modified scale parameter, this again fails at somewhere around the wave height of 2 meters. So this suggests we might want to use a threshold of about 2 meters when modeling extreme wave heights. what we can look at as well is that mean residual life plot, so the expected exceedance size, which is just done using this mrl.plot function. And remember, what we're looking for here is for the mean exceedance size to increase linearly as the threshold decreases. So here we have our point estimate and 95% confidence intervals for the mean exceedance size. And at very large values, these become quite noisy because we're basing this on very few data points. But essentially what you can see is that somewhere around 2 again, we get this sort of elbow happening in the plot, where this linear increase breaks down and we see a more rapid increase in the mean exceedance size. So again, this is consistent with us wanting to pick a threshold of about 2 meters as our threshold value for extreme wave heights. So what we're going to do is exactly the same thing, but for wave surges. So gpd.fit range. The data in this case is going to be wave surge $surge. And we've got a suggested range here to have the minimum threshold equal to 0 and the maximum threshold Umax equal to 0.5 meters. And let's stick with 20 thresholds that we're going to try. So here in the parameter stability plot, things are slightly less obvious than before in terms of how far back we can go, but perhaps somewhere in the range of 0.2 meters is where this potentially starts to break down, although you could argue that you could go further back to perhaps about 0.1. Again, here it's best to pick something that's a little bit conservative, and then you can always go back and redo your analysis with a lower threshold and see if your results are consistent. So what I'm going to do now is just skip ahead past the section where we fit the GPD to wave heights and focus on filling in the wave surge code. Feel free to take some time to look through this yourself. So we can see here we're going to pick that surge threshold in this particular example to be 0.1 meters. So we're just going to set U surge to be equal to 0.1. And then we're going to estimate phi U surge, which is going to be the proportion of surge values that are above our threshold. We can work that out really easily by just calculating the mean of the logical vector, where we say our wave surge values, wave surge $surge, greater than U surge. And if we run that and print out its value, we see that about 35.5% of our surge values are above our modeling threshold. So we're using the upper third, roughly, of the data in our model. To fit a GPD model to this, we're going to replace the your code goes here on line 91 with the code gpd.fit. The first argument here is going to be our exceedance data. So that's going to be wave surge $surge. The threshold here is going to be the height of the modeling threshold that we want to use. I'm just going to drop this down onto another line. And that's going to be U underscore surge. The number of observations per year are 365 because it's daily data. And that is all that we need in here. All of the other arguments we'll cover in a later week. So note here that MPY, the number per year, is the approximate number of observations that you have per year. And getting this correct is going to be really important later when we come back to looking at annual return levels. If you don't put this in, then it's going to assume that this is equal to 365. Whereas if we have a different number of observations, say monthly observations rather than daily, then this will throw up errors in our return level estimates. So running this gpd.fit command, we get this surge fit object, which is a list of 16 items. And this has a very similar structure to the GEV fit models that we saw in previous weeks. And what that means is that we can extract our parameter estimates in exactly the same way. So go surge fit $MLE to get our parameter estimates, the point estimate, the standard errors, again, surge underscore fit $SE will give us that vector of standard errors, and the correlation matrix between them can be found using the covariance matrix and then accounting for the variance of each parameter. So this is just done for completeness to match what's in the notes. So let's just take a look at those. Our point estimates for sigma u is 1.12, and for psi is negative 0.1. So like in many environmental applications, we've got a point estimate of the shape parameter that's negative here. What we're going to do next is use this function plot underscore GPD underscore LLH to plot the GPD log likelihood function around the MLE. And what this is going to do is demonstrate that the two parameters, sigma u and psi, are not independent of one another. So our xstat here is just going to be our x data. So wave surge, $surge. And our threshold is going to be u underscore surge. And we've got the range of parameter values filled in for us already. So creating this plot, what we can see is that we've got our maximum likelihood estimate, which we can add to the plot using this points command. So we want this to be surge fit $MLE. Sorry, you can't just feed this a vector straight away. You have to say that you want the x-coordinate to be the first element of that vector and the y-coordinate to be surge fit $MLE square brackets 2. So then we get our MLE appearing on this plot, and we can see the contours of our log likelihood function around the MLE. And what we see is that these aren't orthogonal to the axes. So our two parameters, there's some trade-off that can be made between them. They don't control independent parts of the probability distribution. To get a 95% deviance-based confidence interval for these, we can look at the contour for this that drops a certain amount below the peak of the log likelihood. So our confidence interval level is going to be the MLE value. So surge fit minus Q chi-square. So we're looking at the quantile of the chi-squared distribution, the 0.95 quantile with 2 degrees of freedom because we've got 2 parameters here. So if we just look at what that is exactly, that's going to be 5.99. Oh, accidentally scrolling. And we want the MLE from here, but we don't want the MLE itself. We want the value of the log likelihood at that point, which is going to be the NLLH element, which stands for negative log likelihood. So remember to pop a minus in front of that. And run that. So we see that we want our contour here to be at 1215, which is going to be somewhere inside this first contour that we plotted before. So again, we can use this plot GPD log likelihood function and use the levels command to set where we want that contour to be drawn. So again, our xstat is going to be wave surge, $surge. Our threshold is going to be U surge. And we want this point to again be at the MLE. So I'm just going to copy and paste that from what we had before. So running these 2 lines. Oh dear. Yeah, I've just forgotten to run line 110 first. So there we go. We get our contour and our point estimate. So what we could do here is increase the range of psi slightly. So we want this to go up to a more positive value. So let's have that go up to 0 instead. Okay, and now we have it. We can see our full 95% deviance-based confidence interval for those pair of parameters. So we've got an idea of what our estimated GPD parameter values are for this model, and we're fairly sure that the shape parameter here is negative. What we want to do is see if that model provides any reasonable sort of fit to our observed data. And we can do that really easily with the gpd.diag function from the ismev package. And what that does is produces a set of diagnostic plots in exactly the same way that gev.diag did. So here it just takes one argument, your fitted model, so that's surge fit. And if I make this much bigger, you can see we get 4 plots here, a PP and a QQ plot, which we see fall fairly closely to the line y equals x, where perhaps not capturing quite the largest values. A return level plot, like we saw before. So again here, the largest values that we observed are slightly above the confidence intervals, but otherwise we're seeing a pretty good fit. And a density plot compared to the histogram of observed values. So overall, between these plots, we can see that we're doing pretty well in describing this wave surge data using a GPD model. And what would be really nice, actually, is if on this QQ plot, we could see whether this variation was within the range that we might expect under the fitted model. If we'd seen just a slightly different data set, then we would see different points around here, and they might not be as far away from the line y equals x. So what we can do is add tolerance intervals to this QQ plot to say where we'd expect points to fall if the GPD model were true. And what we're going to do is, rather than creating this on a GPD margin, we're going to use the probability integral transform to transform our data onto exponential 1 margins before we do that. And the reason for that is that it makes the plot more extensible. So when we come to look at non-stationary modeling later on, we can use the same technique. So to add these tolerance intervals, we've got this function QQGPD, but to use that, we're going to need a vector of threshold exceedances. We can make that really easily just by taking our wave surge $. So these are our surge values minus the threshold value. So U surge. But what we want, if we look at these, then we have lots of negative values in here. So what we're going to do is subset that to only keep the values where that is greater than 0. So in this initial vector, we've got a large number of entries, and here we see that we've come down to emit far fewer entries. So we've got just over 1,000 values now. So this is what we're going to feed in as our vector of exceedances. So x equals exceedances, if I can spell it. The scale parameter, we need to put in our MLE for the GPD scale parameter here. So surge fit $MLE, and we want the first entry of that vector. For the shape parameter, we want the second element of that vector. So I'm just going to copy and paste here. We also require the covariance matrix, so not the correlation matrix that we did before, but something easier to get at. So surge fit again, take the list element that is called cov, and setting this CI or confidence interval input to be true so that we know we want to draw confidence intervals on here. So running this qq.gpd function, we see we get the same QQ plot as before, but now on exponential margins. So these are the quantiles of the standard exponential and our observed sample quantiles. And we can see that this deviation at the top is actually within the range that we expect given our parameter uncertainty. So that's all I had to run through in this video. And what we've seen is the key results from chapters 3.1 and 3.2, and also how to fit a GPD model, assuming that we've got IID observations. Thank you very much for watching this video, and I'll see you next time.